said it was really unusual for two people to share the same birthday, so I'm going to show you the birthday paradox. So what are the chances when you have a group of people that two people share a birthday? Well, it's easier to start by thinking about the probability of them not sharing a birthday. So there are 365 days in a normal year, so the probability of not sharing a birthday is 364 out of 365, because 364 days out of 365 you wouldn't share a birthday. So if there were just two people, that would be the probability that you wouldn't share a birthday. 1 out of 365 would be the probability that you would share a birthday, and that's really low. Now, if we multiply this up, and we have three people in the room, so then A compares with B, A also compares with C, and person B compares with person C. So we have three comparisons. If we have 4 people in a room, A compares with B and C and D, and then B needs to compare with C and D, but B has already compared with A over here, and C, it only remains for C to compare with D. And 5 people in a room, you can see there are more comparisons to be done. So these numbers here are the number of comparisons for these groups of people. Now, this sequence here, for those of you who might recognise it, would be the sequence of triangular numbers. And the sequence of triangular numbers we get by doing the number of people multiplied by that number minus 1. So let's write this down. So we've got number of people multiplied by number of people minus 1 over 2, and that's the nth term for that sequence. So let's just show you how that works. If we've got 2 people, 2 multiplied by 2 minus 1, which is 1, over 2 is 1, and that's 1 here. 3 people, so we've got 3 times 2 over 2, and that gives us 3. 4 people, we've got 4 times 3 over 2, and that gives us 6, and the same with 5 times 4 over 2. So these are the number here, I don't need that there, these are the number of comparisons that we get, and this is how we work it out. So if we knew the number of people, we would just subtract 1 from that, multiply it together, and divide by 2 to get the number of comparisons, if that was for a larger group. So let's go back to our probabilities. So if there are 2 people in the room and 1 comparison, then there's a large probability here that they won't share a birthday. If there are 3 comparisons to be made, we have to multiply, we're doing that probability 3 times, we have to multiply that by itself 3 times. And obviously in maths we have an efficient way of saying that, 364 over 365 to the power of 3. So you can see that that 3 there is the same as this 3 here. Okay, and this is just to the power of 1. So here we've got 364 over 365 to the power of the number of comparisons, which is 6. And then here 364 over 365 to the power of 10. Now, when you have a small number, the probability of not sharing a birthday is still pretty high. So if we take, say, 6 people, for example, and I use my calculator, 364 divided by 365, raise that to the power of 6, that gives me 0.98 or 98%. So that's a high probability of not sharing a birthday. But when we have increased the group size, when we get to 10, then we have 10 times 9 over 2, 45 comparisons, and then we have 364 over 365 to the power of 45, and that gives us 0.88 or 88%. So you've got an 88% chance of not sharing a birthday, and then sharing a birthday, you have a 12% chance. With just 10 people in a room, a 12% chance of sharing a birthday. So let's increase that to 20. 20 multiplied by 20 minus 1 over 2 gives us 190. And then if we raise that to the power of 190 there, we get 0.59, 59%. So the probability of sharing a birthday is 41% with just 20 people. So at what point do we have a 50% chance of sharing a birthday? Well, the answer is 23. So 23 times 22 over 2 gives us 253. And if we raise 364 over 365 to the power of 253, we get 0.4995, which is 49.95%. And so that's just under 50% if we round it to 50% here. So the chance of sharing a birthday is just over 50%. There you are.